Now let's have fun and let's see what it takes to hit the 400-mile-an-hour barrier. What's going on YouTube? Today we're going to be explaining why it's so damn hard to break the 300-mile-an-hour barrier. We're going to be looking at some top cars, so the Koenigsegg Jesko, the Hennessey Venom F5, the very controversial SSC Tuatara, and maybe we'll even look at the Bugatti Bolide. So let's get into it. Okay, so before we start jumping into cars, I do want to break down a couple really basic physics equations. So the two forces that act on cars to slow them down are air resistance and rolling resistance. Air resistance is the much more important one, and it has the formula force of drag is equal to 1/2 times rho, which is the density of air, multiplied by the velocity squared, multiplied by the coefficient of drag, multiplied by the frontal area of the car. So if we use the power equation, power equals force times velocity, we then can create the equation the power needed to overcome that force of drag is equal to 1/2 times rho times velocity cubed now, multiplied by the coefficient of drag, multiplied by area. So just to illustrate this concept, I created 3 simple examples. We're going to calculate the horsepower needed to overcome drag at 100 miles an hour, 200 miles an hour, and 300 miles an hour. I won't go through each one, but you can see the numbers on the screen. At 100 miles an hour, it takes 44 horsepower to overcome drag, and this is for a coefficient of drag of 0.3 and frontal area of 2 meters squared. Same numbers used in each example. At 200 miles an hour, it takes 351 horsepower to overcome drag, and at 300 miles an hour, it takes almost 1,200 horsepower to overcome drag. So based on this simple concept, you can see how as speed increases, you need more and more horsepower to overcome that air resistance because it's actually a function of velocity cubed, and that's why these cars have such trouble time reaching these high speeds, and they really start hitting a wall once they get above 300 miles an hour. Okay, so let's look at rolling resistance. This is the other force that acts on the car. We have force of rolling resistance is equal to coefficient of rolling resistance multiplied by the normal force, and we use our power equation, and we end up getting the power needed to overcome rolling resistance is equal to the coefficient of rolling resistance multiplied by the normal force multiplied by the velocity. Cool. So let's take an example. We have 300 miles an hour as our velocity. We have a curb weight of 1,500 kilograms and a coefficient of rolling resistance of 0.015. So we crunch all the numbers and we get 40 horsepower is what's needed to overcome rolling resistance. As you can see, this number is much smaller than the power needed to overcome air resistance. And so I'm not going to go into too much more detail on this, but just know that air resistance is the much more important factor when figuring out how fast a car will go. I forgot to mention a couple of things. So one is this doesn't take into account downforce and lift. So we're assuming that there's no downforce to add to the normal force or lift taking away from the normal force. And the other thing is the coefficient of rolling resistance is somewhat dependent on velocity. It also depends on the tires you're using, the width of the tires. It's really hard to measure that in the real world, but we're just going to use this theoretical number. Again, it doesn't change much, so it won't dramatically increase this power needed, but these are not perfect numbers. This is just an approximation. So now we know for a car that weighs 1,500 kilograms, frontal area of 2 meters squared, with a coefficient of drag of 0.3, it takes about 1,228 horsepower to overcome the 300 mile an hour barrier. Now's the fun part. Let's look at real world cars. We're first going to be looking at the Koenigsegg Jesko, and let's see how fast this thing can go. So you can see the specs on the screen here. We have a curb weight of 3,064 pounds, drag coefficient of 0.278, which is really low for a internal combustion engine car. This car has a frontal area of 1.88 meters squared. It's not on the screen, but that's been quoted by Koenigsegg. And this car makes 1,600 horsepower. So using all of these specs, let's see how much horsepower this car would need theoretically to break the 300 mile an hour barrier. We want to go 300 miles an hour in the Koenigsegg Jesko. We have our numbers, 0.278 drag coefficient, 1.88 meters squared, and 3,064 pound curb weight. We crunch the numbers and we see that we need 1,005 horsepower to go 300 miles an hour. And then for 330 miles an hour, which is the quoted top speed of the Jesko, it needs 1,418 horsepower. And so you might be thinking, hey, the Jesko has a 1,600 horsepower output. Why can it not go faster than 330 in theory? Well, all of that 1,600 horsepower that the engine's making is not getting perfectly delivered to the wheels. There's something called drivetrain loss. And so if you do the numbers here and you divide 1,418 into 1,600, you could see that maybe the Jesko has a drivetrain efficiency of about 88%. And if you're wondering what the heck's drivetrain loss, why that doesn't make any sense, there's tons of information online. You can go look up drivetrain loss, but the typical rule of thumb is rear-wheel drive cars lose about 12 to 15% of their power that gets transmitted to the wheels, and all-wheel drive cars are more 15 to 18% power loss. Again, those are total generalities. There's tons of factors that go into this, and the Koenigsegg is likely more efficient. So let's go to the drag strip. Here we have the Jesko Absolut set up. We're going to start from 280 miles an hour because I don't want to waste all the time that it takes to get up to the 280. And we have a 2-mile distance. And so let's see what this thing looks like accelerating starting from 280 miles an hour. And we can see it's pulling pretty hard at those speeds, 0.1 Gs. And it'll keep pulling past 300. And it's really at the top of its RPM range here. So it's in 9th gear at 8,200 RPM. And you can see at about 313, 315, it really hits a wall and just starts inching. And that was 2 miles. So all that, in that short amount of time, it just covered 2 miles. If you extrapolate this out to like 10 miles, you can see that the Jesko in this simulation gets to about 320 miles an hour. And that's actually because the drivetrain loss we're using on this car is 15% versus the 12% that we just went over in the example. And so it can't quite get to that 330 that's been quoted. But if we lowered that drivetrain loss to the 12%, we'd probably see around a 328, 330 top speed. On the screen here is a side-by-side spec comparison, the Jesko Absolut and the SSC Tuatara. If you don't know what the SSC Tuatara is, it's a really small volume production car that actually hasn't gone into production yet, but they claim to beat the top speed record and break, I think, the 300 mile an hour barrier, but it was then debunked and they came out and said that they didn't break it. There's a bunch of drama surrounding it, but they're claiming some pretty crazy numbers. So side by side here, we can go down the line. We see 1,750 horsepower, so more power than the Koenigsegg, 3,050 pound curb weight, pretty similar. A drag coefficient of 0.279 versus 0.278. It's hardly any different. They're basically saying it's as aerodynamic as the Jesko, which is a little bit hard to believe. And they're claiming that the frontal area, it's not shown here, but they're claiming the frontal area is only 1.7 meters squared versus the Jesko frontal area of 1.88 meters squared. So in theory, this car is actually more aerodynamic than a Jesko, and the simulation actually shows this. So let's see a drag race. So we set up a race here. We're starting from 280 miles an hour. We have the Jesko on top and the SSC Tuatara on bottom. So we can see the Tuatara, yeah, it's pulling more. It has more power and it's more aerodynamic according to the numbers they've released, which is pretty suspect because I think it'd be really hard to compete with a company like Koenigsegg, who's always pushing the edge of technology and has way more funding and a way bigger track record than SSC. And so obviously the simulation is going to show these results, but in real life, I don't think the SSC is quite as fast as they claim, and we maybe have seen that. But I will say, to not take away too much from them, it's really hard to do top speed runs, and you can see in just this 2-mile distance, already starting at 280 miles an hour, they can't even hit their top speed. And so it just goes to show how hard it is to do these top speed runs in real life. In a simulation, it's easy. You can set up a 10-mile theoretical drag strip and just let them run. But yeah, to hit, I mean, if you're talking about 330 miles an hour, wind is a massive factor. You need a huge straight flat road. Conditions need to be good. Otherwise it's really dangerous. And so another big point of this video is just to show you how hard it is once you get past 300 miles an hour to even make a run like this in real life. Like, there's literally not roads that could support top speed runs like this. So moving on to some other cars, we have the Hennessey Venom F5 and the Bugatti Bolide on the screen. Side-by-side spec comparison, you can see it's pretty similar, about 1,800 horsepower, about 3,000 pounds. But the drag coefficient on the Venom F5, they're saying it's only a 0.39, which is really high. I don't know if it's an error or what, but they're trying to reach a top speed of 311 in this car, and at a 0.39, that's not possible. If you remember back to the Koenigsegg and the SEC, they're talking about a 0.28 roughly, and so this is 0.11 more than that. It plays a huge factor in top speed, and I'm going to show you a drag race and show you why that 311 is out of the question with that drag coefficient. So I set up a race from 250 miles an hour this time. We have that Venom F5 on the top and Bugatti Bolide on the bottom. And so from 250 miles an hour, let's see what these cars can do. So we can see the Bugatti is already pulling a lot harder, and the Venom is already hitting a wall. So at about 290-ish, let's say, the Venom is really slowing down, and that it's because of that really high drag coefficient of 0.39. It's basically hitting top speed at about 293 miles an hour here, and that 311 miles an hour they quoted is just not going to be possible with this drag coefficient. And so I don't know if it was like a press release error or the specs they have are incorrect on their website, but I think their drag coefficient is going to be lower than that. I think it'll be in the low threes because 0.39 just seems too high. Maybe they'll have a low drag version and a track version, but I'd imagine that the drag will be lower so they can reach that top speed. So we've spent some time looking at the physics, looking at some top cars. Now let's have fun and let's see what it takes to hit the 400 mile an hour barrier. Okay, so we're going to see what it takes to get the Koenigsegg Jesko to 400 miles an hour. So first thing we're going to do is lower the drag coefficient from 0.278 to 0.2. And then because we're running out of RPMs in the ninth gear, the final gear, we need to make the gear ratio a little bit lower so we can have more RPMs to work with to get to a higher top speed. So we're going to lower the ninth gear ratio to about 0.6. We're going to save that, and we're going to see what this thing does with the drag strip. On top, we have the modified version with the low drag coefficient and the longer final gear. And then on the bottom is the stock version. So off the bat, you can see it's already pulling much harder, and it's going much faster. So it's already at 315, and it's still pulling. You can see that last gear is much longer, so it's at lower RPM, but at a higher speed. And in just 2 miles, granted we did start from 280, it's hitting 340. So let's keep pushing this and let's get that 400 mile an hour mark. Okay, so we already lowered the drag coefficient to 0.2, and that's incredibly low. And I don't want to make this too unrealistic. And so I'm not going to lower the coefficient of drag anymore because that's pretty close to a theoretical limit for a road going car. Right now, the Tesla Model S has a drag coefficient of 0.208, which is incredibly good, and that's for an EV. This is for an internal combustion engine car, which needs a whole lot more cooling and has a whole lot more radiators. So let's instead increase power. So the first thing we're going to do is give this thing about 2,500 horsepower, so 2,460 horsepower. And let's see how this thing does with the drag strip. I've set up a drag race. It's 5 miles long, so these cars look like ants, but they're the cars. On top is the modified version. On bottom is the stock. So the modified version now has a 0.2 coefficient of drag. It makes about 2,500 horsepower, and then we extended the final gear so we can get to those top speeds. And as you can see, it's pulling like crazy. So it's already at 370 miles an hour, and it's still pulling. So at this point, we can see it should reach the 400 mile an hour mark, and it's passing the halfway 2.5 mile mark. And yeah, it's slowly approaching 400. It's about to hit it, and there we go. So 400 miles an hour. This took quite a bit. I just went through what it took, and it goes to show how hard it is for these cars to just keep getting faster and faster and faster. And the 300 mile an hour mark is already such a hard barrier to get through. I think it's going to take a lot of years for cars to get up to even coming close to the 400 mile an hour barrier. Another thing that I didn't talk about in this video is tire technology. And all street tires are rated for a certain speed. And the best tires that have the highest speed rating aren't getting much above 300 miles an hour. As far as I know, if you know otherwise, share in the comments below. I'd love to learn about it. But it's really hard for tires to manage all that heat at those high speeds. And so there needs to be some big improvements in tire technology before we can start breaking these barriers. So if you've made it to this point, I really appreciate you watching the video. If there's one thing to take from this, I think it's how important air resistance is for cars. It's basically the one determining factor in how fast it can go, how efficient it is, all those kind of things. Even if you look at an economy car versus a pickup truck on the highway, you can see why the economy car is so much more efficient, and that's because it has a lower frontal area, it probably has a lower drag coefficient, and it's able to just use much less energy to go the same speed. And all that can be determined from that air resistance equation, which has velocity cubed. And so that also tells you that as speed increases, it's going to just take more and more and more power to hit those speeds. So yeah, I hope you guys liked the video. If you did, make sure you like and subscribe. I'll be doing plenty more of these videos coming soon. I really enjoy making them. I hope you got something from it, and I'll see you guys next time.